Hi everyone. This is our first theory lunch. So today we have Mingxun Zhou to talk about optimal single server private information retrieval.
So hi everybody. I'm Mingxun. I'm a third-year PhD here. My advisor is Ling Shi and Zhu Yaofanti. I'm working on cryptography, differential privacy stuff. And today I'm very happy to share with you our new work on optimal single server private information retrieval. This is a joint work with Wei-Kai Lin, who is now a postdoc in the Northeastern University, and Yannis is now a postdoc here, and my advisor, Ling Shi. All right, so before we talk about private information retrieval, let's talk about what is non-private information retrieval. So this is actually our theory lunch host, Jeff. He is not here today, but basically he wants to play some Minecraft before he finishes his paper writing. So to be able to do that, he needs to fetch the IP address from the DNS server. So you query what is the IP for Minecraft.net, and the DNS server returns the IP for Minecraft.net. However, the DNS server is compromised by his advisor Pravish, and now Pravish can see that Jeff is trying to access the IP of Minecraft.net. So basically, Pravish is not very happy. He said, "Okay, did you finish your paper?" Okay, this is just a stupid joke. But now, in private information retrieval, in some sense, we can think about the query to the DNS server is somehow encrypted, and also the response is kind of encrypted. So basically, the DNS server learns nothing about the query from the client. And now even Pravish can compromise the DNS server, still Pravish can learn nothing about what Jeff is trying to access. Maybe Jeff is trying to access overlib, right? So in short, PIR stands for public database and private query. It has a lot of applications like private DNS server, blacklist website, private set intersection, contact discovery, so on and so forth. All right, so before we jump into our technical session, I just want to make a promise here that although this talk is about cryptography, the algorithm design itself is not super related to cryptography. So if you're not familiar with cryptography, it's totally fine. I can assure you that the algorithm design part is very understandable. All right, so in the classical model of PIR, we assume there's no preprocessing phase, and also the server stores a database in plain text. Here, we basically assume the database is like an n-bit array. So basically, if you access one index, it returns a bit. So there's actually a very trivial naive scheme in the classical model. So basically, whatever the client is querying, it simply said, give me the whole database. And it downloads the whole database in the local. And this scheme trivially satisfies privacy because no matter what you are querying, you simply download the whole database, right? But this is a very, very terrible scheme because now you can see the bandwidth consumption will be linear in the size of the whole database, and also the service computation time will also be linear in that. So this is a truly terrible scheme. Using fully homomorphic encryption, yes, we can improve that naive scheme that basically now this client can encrypt its query to the database, and the database can perform homomorphic encryption searching, and then, but it's still linear searching, and then it returns the encrypted response to the client. So now you can see that the bandwidth will only be polylogarithmic size, and the client time is also improved to polylogarithmic, but the server time will still be linear in n. So here we use the tilde-O notation to hide all the logarithmic factors. So basically in classical PIR, the downside of classical PIR is it has linear time scanning, but the good thing is it has pretty small bandwidth consumption. So basically the bandwidth consumption will be polylogarithmic. So can we design a PIR scheme with sublinear server time? Unfortunately, this is hopeless in the classical model. Try to remove it a little bit.
Sorry about that.
Okay, that's fine. So it's hopeless in the classical model. So basically, there's a well-known lower bound from Bimo, Ishai, Melkin, 2000 paper, saying that the server time will always be omega n in the classical model. So how can we defeat this lower bound? In their paper, they propose a pretty nice idea about preprocessing PIR. And in this model, we can actually achieve sublinear server computation time. And notice that why do we need this preprocessing model? If you think about for each query, you need to scan the whole database. Like if we're running a DNS server for a PIR, then basically the DNS record will be like gigabytes big, right? So for each single query, you need to scan the whole database, and it's totally impractical. So that's the reason why we need sublinear PIR. And I'm going to talk about this specific preprocessing model here. So basically, the client in the preprocessing phase, it's going to interact with the server. And at the end of the preprocessing phase, the client is going to download some hint to its local storage. And the client just stores those hints and use those hints. The client can make multiple queries during the online phase. And using those hints, the client can make the online query pretty efficient. So this is the preprocessing model. And in the preprocessing model, we can actually get sublinear time. In fact, the best previous work achieves like roughly square root n time per query, assuming the hint size will be square root n. So basically, you need to download some square root n bits in the local. The downside of the previous best work is that the per query bandwidth will be pretty large, that the consumption will be square root n. So that's not what we want. Can we achieve the best of both worlds? And in our paper, we try to answer this question. And our paper says, yes, we can actually get the best out of both worlds. So basically, we can achieve that sublinear time and also achieve that polylogarithmic bandwidth per query. And this is actually optimal. So in the previous work, they actually show that the multiplication of the server computation time per query and the number of bits stored in the client storage, the multiplication of them should be omega n. So in this sense, our work is optimal up to some logarithmic factors. All right, so in this talk, although our final result, as you can see that down right here, our final result is a one server PRR scheme that can support unbounded number of queries during the online phase. But in this talk, I'm going to focus on a simpler version, that is the two server PIR that can support only bounded number of queries. And in fact, the transformation from the two server PIR scheme with bounded queries to the one server PIR scheme that can support unbounded queries, I'm going to talk about this transformation briefly before we dive into the technical details. And okay, any questions so far? Okay, great. All right, so the first transformation is that how can we get a PRR scheme that can support unbounded queries during the online phase from a bounded scheme? And the technique here is pipelining. So in the bounded model, basically the client runs some preprocessing with the server. And in the online phase, the client can only query, for example, let's say up to square root n queries, so it's bounded. And in the unbounded model, basically the client runs the preprocessing phase once, and it can query like unbounded number of queries. And how do we do that? Let's assume we have a pretty good bounded scheme. So basically in the bounded scheme, during the online phase, we can support up to square root n queries. In the preprocessing phase, we can run it in linear time and also square root n bandwidth. Okay, so if you do the amortization, you can see that the per query bandwidth will be polylogarithmic, and the per query time will be square root n. And then we simply stack them together. Let's say we stack the second instance of the bounded scheme, and we run the preprocessing phase of the second scheme in parallel with the first instance online phase. Okay, we stack them together. and we keep doing the stacking. This is somehow like doing pipelining in like computer architecture or something like that. And now, as you can see that the true preprocessing phase is only the preprocessing phase of the first instance. And everything else, we can think about them as the online phase. So in the online phase, you just keep querying, query. But in parallel with the query, you run some preprocessing competition, something like this. So by doing this stacking and pipelining idea, we can go from bounded queries to unbounded queries. All right. And the second transformation I'm going to talk about is how do we get from 2 server PIR to 1 server PIR? So what does it mean by 2 server PIR? So basically in the 2 server PIR, we assume there are 2 servers, and each server stores a copy of the database. And very importantly, we assume the 2 servers never talk to each other. So they're independent, they're separated, and they would not collude together to break the client's privacy. So you can think about like one server is run by Google, one server is run by Apple, and they are competing with each other. So they will not collude to break my privacy. So this is the idea of 2 server PIR. So in the 2 server PIR scheme, you can see that during the preprocessing phase, the client only interacts with here, let's say the blue server here. And it runs some preprocessing algorithm. And during the online phase, the client only interacts with the red server here, and the client makes some queries. So this is a 2 server PIR. And we simply use fully homomorphic encryption to encrypt everything during the preprocessing phase. So basically now, whole preprocessing is run inside of some fully homomorphic encryption scheme. If you're not familiar with fully homomorphic encryption, you can think about we can evaluate probably every computable function in an encrypted way, but when that's only doable when you can represent a function using a circuit. So you need to write a function down as a circuit, and then you evaluate the circuit. So basically, we can use FHE to compile everything and encrypt everything. So now, even the preprocessing blue server can learn nothing about the client. And why do we need that? The reason is, since we run everything inside of the encryption, so basically, no matter, it's actually okay that the preprocessing server is the same as the online server. So now we only have 1 server here. Okay, so that's the transformation. We can transform a 2 server PIR to 1 server PIR. There are actually 2 key requirements for this transformation. First thing is we can see that the scheme is fully separated. So basically the preprocessing phase and the online phase is fully separated. And the second key requirement, this is very important, that we need to be able to represent the preprocessing algorithm in a quasi-linear size circuit. So originally, we measure the time in the RAM model, right? So in the RAM model, you can access some random memory location. But in the circuit model, it's not that easy. You cannot just simply access a memory because everything now is a big circuit. So you need to be able to transform the computation to a circuit representation and do it efficiently. And due to this reason, the previous best work on the 2 server PIR cannot use this transformation. The first reason, you can see that they are not fully separated. So actually the client talks to the blue server also during the online phase, right? So this is not fully separated. And the second reason it cannot use this transformation is that if we try to use FHE in this scheme, basically during the online phase, per query, the blue server will run some algorithm that runs in squared n time. But this is measured in the RAM model. And if we measure it in the circuit model, it's going to be linear size circuit. And this is not okay, because if for each query, you need to evaluate the linear size circuit, basically the per query time is linear. So it defeats the purpose about sublinear PIR. So it's not okay. So in this talk, I'm going to talk about how do we design a two-server PRS scheme that can satisfy our key requirement. And also we need to design it in an efficient way. All right, so any questions so far? Okay, let's move on.
I have a question.
Sure.
Why is it if you need to query the blue server in the online phase, the circuit has to be large in the online phase?
Okay, so the reason is in the original algorithm, our online phase is like we need to, the blue server needs to calculate some parity of some skirt and location. And to be able to do that, basically you need to perform skirt and memory access. However, if you represent it using a circuit, basically there's nothing you can do rather than just write down a linear size circuit and let the circuit to collect the value. So that's the reason why there's actually a gap between the RAM model and the circuit model. Hey, go ahead.
I was just going to say, could you say what the model is one more time?
The two server.
Yeah.
Okay, so the two server is we have two server. They all store a copy of the database, and they are separated, so they will not collude together. So you can think about like one is Apple, one is Google, so they will not share data. That's a model. It's actually a stronger assumption because in the one server scheme, the Google can run it itself, but now in the two server scheme, Google need to cooperate with Apple, right? So this is a stronger assumption.
This means that like one of them, like when you're doing like the proof that this is secure, like you have to consider what happens if one of them.
Yes.
But not.
Yeah, not the joint view of them. Yeah. Okay, go ahead.
Can you explain the separated requirement again? Does it mean that only one server can be in the pre-processing?
Yeah. So basically, you can see that during the pre-processing phase, we only talk to one server, and during online phase, we only talk to another server. So this is like separated. So the fully separation requirements allow us to have an easier transformation. Actually. Well, this is actually, I would say, not 100% necessary, but it's much easier for us to do the transformation.
So, so if we don't do pre-processing with like the red server, for example, then during the online phase, isn't it like we just do no pre-processing with the red server, and so it's like just classical PIR?
Not quite, because if you can download something, so just a very terrible idea, but this is just for explanation. So let's say in the offline phase, you just throw out some random access. You throw out some random access to the blue server and you collect them, right? So during the online phase, if your query, you already know what's the value of your query is, then you can save some work. So this is like why preprocessing can save you some work. But this is not a good algorithm actually. But this is just explanation why preprocessing can help you.
This full separation is actually efficient to the time. It's because it's online. You need to do this FAQ transformation. It'll blow up the square root n linear. Because the square root n in the two server case in this scheme is like in the RAM model. So it's more like efficient. Oh, it's not about security.
Oh.
All right. So, okay. So this talk we're going to focus on how to design the efficient two-server PIR that can support bounded queries. Okay. And here's our roadmap. So I'm going to first describe an inefficient strawman scheme. This scheme doesn't have anything related to crypto. It's just pure algorithm design. I hope every theory student can understand that, actually. And then we're going to use some cryptography to improve that scheme to the efficient two-server scheme. And finally, I'm going to briefly mention about the proof. So basically, before the proof, everything should be understandable, I think. The proof itself is, quite complicated. So, all right. So this is our inefficient two-server strawman. So in the preprocessing phase, what the client would do, it first sample square and sets. All right. So each set will contain some index from 1 to n. And In each set, each index will appear independently with probability 1 over square root n. So roughly each set will have size square root n, right? Because each one of them will appear with probability 1 over square root n. And then the client store all those sets in the local. And then the client send all those sets to the preprocessing server. And the preprocessing server take all those sets and return the parity of those sets. So the parity of those sets simply means you take the corresponding location of them. Remember, each location stores a bit, right? And then you take the XOR sum together. That's the parity of those sets. And then the client learns those parities, and the client stores those sets along with their parities. And now you can see that the client local storage is actually very big because we have square root n set. Each set contains roughly square root n indices, so it's pretty big. It's like roughly n. And I promise you that we are going to improve that later. Okay. And now, how does those hint can help us during the online phase? So here's our online algorithm. So basically, when we query, let's say we are querying index 3, and the client first will find the first set that contains 3. Okay, so here it finds a set 1, 3, 16 that contains 3. And then it sends the set, but it would delete 3 from this set and send the remaining set to the online server. And the online server return the parity of this set. And then what the client would do is simply take the XOR sum of these two parity, because the parity of 1, 3, 16 XOR the parity of 1, 16 will result in the parity of exactly the answer for 3, right? So actually, I want to ask you a question. This scheme has a very terrible privacy problem with respect to the online server. Can anybody see it? So the online server can learn some non-trivial information about the client's query. Go ahead.
The server can store the sets.
And then?
So it knows 1, 16. You can know which query is this.
Okay, go ahead.
If you made repeated queries on the same set, so for example, your first query was 116,
Uh-huh.
and then your second query was 1, 3.
Okay.
Now you know that 3 and 16 are both in the same set, so the first query must have been for 3 and the second query must have been for 16.
Okay, that's okay, but I promise you we will not make, so basically if we use one set, we are gonna throw it out. So
Okay.
Go ahead.
It knows it's not 1 or 16.
Okay, that's the answer, actually. So this is actually very simple, right? So because you always delete 3, the server is gonna know that it's not 1 or 16, right? And how do we fix that? The answer is simple, that instead of deleting 3 directly, we resample 3. So remember that we draw each index with probability 1 over square n. So we just simply redraw 3 with the same probability, okay? And now it turns out that this set, in the view of the online server, this set is uniformly random. You can think about, we find a set that contains 3, and now we just resample this condition. And now this set is indeed uniformly random, and the online server can learn nothing. Okay. This fix will introduce some small error probability. That's because if you resample 3 and with some bad luck, 3 is indeed kept in that set, then the parity you learn from the online server will be exactly the same as your local parity. So basically learn nothing, right? So to like boost our success probability, we run k-parallel instances and just perform a majority voting. And if we have polylogarithmic parallel instances, then we can boost basically the error probability to negligibly small. Go ahead.
Sorry, aren't, maybe I'm not understanding what resampling is. Like,
Mhm.
aren't you like taking the answer you wanted and XORing it with like a random bit? Like, because is what you want to get the XOR of 1 and 16?
Yes, that's
That's what you want, but then if you XOR it with like the bit, a random bit from the database, then how do you get
Oh,
Not resampling the-
yeah, we are not resampling the whole set. So resample 3 just means we resample that 3 point, that particular point. We sample that, we throw a coin with Bernoulli distribution that with probability 1 over square root n, we keep 3 in the set. Otherwise, we delete 3. So basically, this set will always be a subset of your local set.
You're not resampling the database. You're only resampling the decision whether you want to send to
Yeah.
the server or not.
So in our talk, because we always use the tilde notation, we don't really care about the log n factor. So we can just run parallel instances and perform majority voting to like get a negligible error probability. So I talked about we cannot reuse the same set. Otherwise, just like he said, that we will leak some information. So after we use that set, we need to refresh the sets. Okay. So basically, we want to replace that consume set with another one. To be able to do that, we slightly change our preprocessing phase that we additionally query the parity for squared n backup sets. And then after we store all the backup sets in the local storage, and it doesn't change the asymptotic behavior. And after we finish one query, we simply promote, just pick one from the backup set to the primary set. Okay, and now we just call it a refresh. And actually, there's one very important detail here. That is, we need to manually add 3 into our promoting set. The reason why is that we already consume a set. We say it's a random set subject to 3 is in the set, right? So now to be able to maintain the distribution, we need to add a random set subject to 3 is in the set. So that's the reason why we need to make sure 3 is in the set. So if 3 is not in the set, we can manually add it because we know the database value for 3. We also know the parity for the remaining element. So we can just simply run the local computation and get the correct parity. Okay. Okay, now let's talk about why this scheme is private. So basically, you can see that during the preprocessing phase, the preprocessing server learns a bunch of random sets, and during the online phase, the online server also sees a bunch of random sets. So basically, they all learns nothing about the client query. Okay. So yeah, each server sees uniformly random sets. Oops. Hi, go ahead.
Is it like actually uniformly random or is it only statistically?
Let me think. It should be uniformly random. Okay, so let's review our inefficient strawman scheme. So basically, our storage, the bad thing about the scheme is that during the preprocessing phase, we need to send all those sets, and sending those sets consumes like linear bandwidth. And also the client needs to store all those sets. So it also store like linear side thing. So it's not good. And to improve the set, we see the main idea here is that the strawman scheme needs to represent a set with like squared n bits. So we store them all together, right? However, there's actually a very simple there's actually an idea that we can represent a set with a very short size key. So if you think about it, we use some hash function to generate a set. So now we can have a very short key, right? So this is actually the idea from the previous paper from Shi et al. It's actually a paper from Lei. All right, so with this idea that we represent the set with a short key, let's see what's our efficient to server scheme. So basically, now instead of sampling all those sets, the client simply sample all those keys and they send those keys to the preprocessing server. The preprocessing server use those keys and expand them into the set and calculate the parity and return the parities to the client. And now the client simply store those keys instead of those original set. And it also store those parity. And now when the client needs to make a query, like query index 3, it needs to find a set including 3, but now it cannot simply perform, it needs to do the membership testing with respect to the key instead of the whole set, okay? And then remember, we need to do the resampling to ensure our privacy. So we need to do the resampling on the key instead of the original set. And then the client simply sends this key. And during the refresh phase, the client needs to promote the backup key to the primary, and you need to manually add 3 into that set. Okay. So now that's actually just our efficient two-server scheme. And actually, if you analyze the asymptotic behavior of that scheme, you can see that the preprocessing phase, because we only send those keys, now the bandwidth is improved to be square root n, and the storage is also improved to be square root n. And during the online phase, the client simply sends 1 key to the server. So per query, you only consumes polylogarithmic bandwidth. And also, the server computation time will also be very efficient. So that's our efficient two-server scheme. And now everything comes down to how do we design our representation about a set, right? So the representation is the key idea. So what do we need from the key K? First thing is the server needs to be able to enumerate a set, right? Our set will have roughly size square root n, and we want to have a fast set enumeration algorithm on those keys. So basically, if we have a square root n size set, we want to enumerate it in time square root n instead of scanning the whole index n. That's fast set enumeration. And second thing is the client needs to find which key to send to the server, right? So the client needs to find which key contains that particular query index x. So to be able to do that, we also want the key to have a fast membership testing function. Thirdly, remember that we need to perform the resampling operation. So basically, we want the key to support resampling of a particular point. So that is very special. And also, we want this resampling to be private. So basically, when the server sees this resample key, it cannot tell which point is resampled before. So it cannot, if 3 is kept in this set, then basically the server sees 1, 3, 16 the same way. Okay, okay. So it's private resampling. And the final thing is adding. So remember that when we refresh the set, we need to add 3 to this to the set. So basically we want a adding operation, and this also needs to be private. So these are the 4 requirements we need to have for our special set representation. All right. So there's actually a naive way to represent sets. The naive way is very simple. We take a pseudo-random function with respect to some key, and if x is in this, so when the pseudo-random function value on that particular point modulo square root n is 0, then we say that particular index is included. So this happens with roughly probability 1 over square root n, right? This is very straightforward. And this algorithm has a fast membership testing algorithm, right? It's very straightforward. You simply take the PRF value modulo by square root n and check whether that value is 0 or something else. So it's fast. However, the set enumeration algorithm is very slow because there's actually no better way than doing linear scanning of 1 to n and check each one of them, are they included? So it doesn't have a fast set enumeration algorithm. And it's actually not quite easy to reconcile them. So here, I introduced a very clever idea from the previous Shi et al. Paper. They construct a object called pseudo-random set. And here's how it works. It can actually satisfy fast set enumeration and fast membership testing. So let's say the index we care about is 13. And we write it down as a binary representation. Okay. And the first thing we're going to do is we pad 2 log n zeros to the end of the binary representation. And don't worry too much about this padding. And second thing we're going to do is we're going to look at the prefix that has length larger than half log n. And we're going to use that pseudo-random function and somehow like hash that prefix to a single bit. And we ask whether that single bit is 1 or 0. And we simply look at the hash value for all the prefixes longer than half log n. And we say if x is in the set, the requirement is all the prefixes longer than half log n need to be hashed to 1. And if you take the probability will roughly be 1 over square root n times log square n. Okay. Okay, so this is our set representation. So each index is included in the set using this. We use this algorithm to check it. Right? So this is our representation. And why is this good? Because first, very obviously that it has a very nice membership testing algorithm. You simply run the pseudo-random function on all those prefixes. You check, are they all 1? And if they are all 1, then it is in the set. Otherwise, it's not in the set. So this is very fast. And also, it has a very nice fast set enumeration algorithm. It works like this. So first, we just keep all those prefixes that has size half log n. And then in each expansion, we simply pad 1 bit to the end. Right? So we pad 1 or 0 to the end. So each one prefix will be expanded to 2 string, right? And then we use the pseudo random function to evaluate all the new expanded prefixes. And then we see, okay, the last one is the PRF value is 0. Then we simply delete it from our active set here. And then we keep all the remaining things. And then we keep doing the expansion. So this is the algorithm until we reach the binary representation length. And then we stop. And then we pick all of them. And the remaining binary representation is exactly the indices included in our set. Okay. So why is this very efficient? One reason is that basically there's a very simple lemma that in each active prefix set, the set size is not going to be larger than the final set size, right? Because you simply take the prefix of them, something like that. So it's not going to be larger than the final set size. And also you think about, you only do log n expansion time, right? So basically the complexity of this algorithm is exactly log n times the size of your set. So this is very efficient. All right. So now it satisfies the 2 requirements. However, it doesn't tell us how to do resampling and how to do adding, right? And the key idea, so in our paper, we solved this problem. The key idea in our paper is to use privately programmable pseudo-random set. We construct this object based on privately programmable PRF. And this part will get a little bit technical. So here I'll go through some definition about privately programmable pseudo-random function. So basically, we would generate a key k of the pseudo-random function. So pseudo-random function, you can think about just a hash function. And it has a very special operation called programming. So basically, we can manually control some of the outputs in the pseudo-random function. So basically, we have multiple point value pairs, and we simply program them into the key. And after the programming, we would generate a new key, k prime. And what happens if we evaluate on this new key, k prime? So if your evaluation point has been programmed before, then it's going to output the program value. Otherwise, it's going to return the original pseudo-random value. So in some sense, it's like you can manually control some output of some points in the pseudo-random function. So it seems very, very, very powerful. Okay. And also, we need some privacy guarantee of this cryptography object. So basically, we want that your program key can hide the program point. In some sense, we program some points on the pseudo-random function, and we don't want the server to tell which point have been programmed before. So basically, we want to hide all those program points. privacy property about the privately programmable pseudorandom function. And then with that programming idea, doing adding turns out to be pretty straightforward. That original, let's say 13 is not in a set. So basically some prefix is not hashed to 1. And we simply just program them to be all 1. Right? Just manually change the outcome of the PRF. And then after changing, we have a new key K prime. And we simply have that in this new key K prime, when we evaluating all the prefixes of 13, basically they're all 1 because we manually changed them. Right? And now 13 is included in the set. So this is how we do adding. Okay. And how do we do sampling? Can anybody tell us, like, how do we do sampling? It should be like very, very simple. Yeah, basically you just do program one more time. So basically, original if 13 is included in set, and we simply resample the outcome of the prefixes, and now that's a resampling. So basically, we resample the output for the prefixes, and in some way, 13 is resampled, and that's done. So basically, we have a new key K prime, and in this new key K prime, 13 is resampled using the programmer. There's one last caveat. So basically, the programmable PRF only supports one-time programming. So you cannot program it one time and then program it again. So, but in our key, remember that we need to adding and do resampling. So how do we do that? So the idea here is to have a lazy operation. So during the first time we do the adding, we don't do the adding, we don't program it during that time. We simply just like write down, we are gonna add 13 there, and it's done. And then during the resampling phase, we do the programming during the resampling. So we do the programming at that time, and because we already marked down that 13 should be included in the set. And during this time, we program our note to the PRF. So by doing this lazy operation, we're able to use one-time programming to do add and resample. All right, let's go over our scheme again. So after this slide, we're gonna get into the proof. So basically, in the pre-processing phase, the client simply send like 2 squared n keys to the server. The server used the fast set enumeration algorithm and return the parity. And the client simply store all those keys in its local storage along with those parities. And during the online phase, when we query for X, we find a key such that X is included, and then we send the resample key to the server. The server return the parity, and the client do the refreshing that it promote the backup key to primary and add that particular point to the key. So this is our whole scheme. And it is very efficient. I'm going to show some performance later. So any questions so far about the construction?
Does adding X to the key, like how much does the key go by?
So during that time, remember we are doing lazy operation, right? So during the adding, we are not expanding the key. So actually in the programmable PRF, you need to have a predefined length L. So the length L is how many points you can program. So that's an upper bound. So basically, before programming and after programming, the key doesn't grow. So basically, you already keep some space for it. So you can think about before you do the programming, there's a bunch of empty space, and after programming, the space is filled up. So basically, the key size doesn't grow, but you need to predefine how many points you're gonna program, and that is actually okay in our construction because we already know how many points we're gonna program.
So all the keys are abstract, poly in log and security planning. So poly log lambda.
No. All right, so I think we have roughly 10 minutes. I'll just quickly go through the proof. If you don't understand, it doesn't matter. Okay, so now if we look at the asymptotic performance during the preprocessing, since we only send the keys, we send square n keys, so the bandwidth will be square n. The offline server, sorry, the preprocessed server uses the fast set enumeration algorithm, and it can enumerate them one by one. So it simply run in linear time, and now the client only store square n keys, and the key is very short, so the storage is also roughly square n. During the online time, we send one key per query, so the bandwidth is also very small. And also, the online server simply expand those keys using the fast set enumeration algorithm, and it also runs in square n time. And finally, it satisfies full separation. So basically, it satisfies all the key requirements we need. And one last touch is that indeed we can represent this algorithm, this preprocessing algorithm, using circuit model, and we can efficiently represent it using a quasi-linear size circuit. So this part, I'm not going to go into the details. So if you're interested, you can take a look at the picture. Take a look at the paper. Okay. All right. So that's basically everything about the construction of the algorithm. All right. So we have roughly 10 minutes. I'm going to quickly go through our proof. So if you don't understand it, totally fine. So it turns out that although the algorithm design looks like it doesn't contain very complicated thing, but we still need a new proof. And the challenge is that first thing is the private definition of the our building block, privately programmable PRF, is far away from what we need. And we need to build multiple key lemmas, multiple intermediate key lemma to get to a form that we can easily use in our privacy proof. And the second thing is, in our final construction, we have crypto thing. We have cryptography about FHE. We have cryptography about the PRF. And we also have some probability analysis. So basically, we want to analyze the set in the local. We want to analyze a set seen by the server. So it's quite complicated. And there's one key lemma. So the key lemma says something like this. So basically, P1 is the points that we want to program to be 1. So basically, that's represent the adding operation. And P2 is those points that we want to resample. Right. So we have the point value pairs set in P1, in P2, and we resample all the values Y1 to YL. Okay. And in the real world experiment, we're going to first generate the key and then use the program to program the adding and resampling operation to the key. And in the simulated experiments, instead of doing programming, we have some simulation algorithm that can generate a key, and we keep doing reject sampling. So we keep sampling, because in each time you run the sampling, you're going to have a new key, and you simply take the key and check all those program points. And if you're very lucky that in some sampling that all the program points are satisfied, then we output the key. So the first one is a real experiment. The second one is simulated experiments. And in our paper, we are able to show that these two experiments are computationally indistinguishable. All right, so using that key lemma, we are able to decouple the crypto and probability analysis. So remember that our crypto object will be FHE and also the privately programmable PRF. For the probability analysis, we have the set stored by the client. We also have the sets observed by the server. So we also need to analyze the distribution of those sets. So using the key lemma, we can separate them and then analyze them one by one. Okay. All right, so basically that's it. So final recap here. So we have the transformation from 2 server scheme to 1 server scheme. And the key requirement is that we need to have full separation and also the quasi-linear size circuit for preprocessing. And we designed an efficient 2 server PRF scheme that satisfies those requirements, that we construct a new crypto object called privately programmable pseudorandom set. And this PRR scheme runs within polylogarithmic bandwidth per query and square root n time per query. So, all right, it seems pretty good. We actually achieved the gene asymptotic. So that is basically the best we can hope for, modulos and polylogarithmic factors, actually. But one last thing is that our scheme is not practical, actually, because our scheme, we use FHE to evaluate privately programmable PRF. So basically, FHE itself is a very, very heavy cryptography object. And also the programmable PRF is also very heavy. So we are stacking two very heavy crypto objects together. And it's very, very difficult to implement, and its real world performance will be not very great. So, so here the open question is, can we really design a practical sublinear one-server PIR? So in theory, in our paper, we say, yes, you can actually have very, very good asymptotic behavior, but we still don't know whether we can make it practical. All right, so that's all about my talk. So thank you, everybody. All right, go ahead.
Going back to the simulator.
Okay.
So that runs exponential and all, right?
Yes, and L will be polylogarithmic.
Oh, right.
No, L is just.
Yep.
3 times log, so this transformation polynomial.
Yeah. So the simulated can run a polynomial. Go ahead.
So improving this lemma, you just use the fact that it is privately programmable, right? Like you don't have to open up what the instruction actually.
Yes, so basically they provide actually two privacy theorem, and they basically says quite slightly different things. And we need to use, so basically we treat the privately programmable PRF as a black box, and we use its API. So basically it provides some privacy guarantee, and we need to use, we don't have to open up the box. We just used its privacy guarantee theorem to prove our key lemma.
Yeah, and it's not that we construct it from LWE.
Yeah.
Any more questions?
Well, okay, if you are interested in this work, you can also talk me like offline. It's total.